Good morning and welcome to this introductory video where I will guide you through the hands-on session of unsupervised learning. You might have already seen a previous lecture where I described some of the most popular unsupervised learning techniques. In this hands-on session, we are going to deploy these techniques on a material science dataset, and in this video I will give a brief recap of the techniques that have already been described. So let's start first with clustering. We have seen a number of algorithms, so let's start with k-means, that is the most popular. We have seen that k-means is a partitioning algorithm where you already know in advance the number of clusters and it associates each point to a specific cluster. This algorithm has a number of problems. One is that clusters are convex and they all have essentially similar shapes. On the other hand, we have also seen that k-means is extremely fast, so it is still very much used. We have seen hierarchical clustering. More specifically, we focus on agglomerative clustering. This deploys dendrograms for inspecting, for a visual inspection of how the different clusters are constituted. In agglomerative clustering, you initially have all points in its own cluster, and then at each iteration clusters are merged according to a linkage criterion. We have seen two different linkage criterion that are going to be covered also in this hands-on session, which are the word and the single linkage. On the other hand, we have seen that the hierarchical clustering also scales quite badly with large data sets. Then we have seen one of the most exemplary density-based algorithm, dbScan, which is based on the assumption that clusters are composed of points in high-density regions and are separated by low-density regions. The low-density regions constitute the noise, so dbScan is able to detect noise, and is also able to detect clusters with different shapes and size. On the other hand, also dbScan we have seen has a number of problems. So it uses a number of parameters, uses essentially two parameters that are not necessarily easy to evaluate. And we also have seen, more importantly, that it's not able to detect clusters with very different density. Then we have seen HDBScan, which is a hierarchical extension of dbScan, and that solves some of the dbScan problems. So it uses intuitive parameters, only one is essentially required, and it is able to extract heterogeneous clusters, so with very different density. Lastly, we also are going to deploy in this hands-on session a new algorithm that was not covered during the lecture, that is density peak, DenPeak, which is also a density-based algorithm that has quite simple behavior. So it identifies the peaks of high-density peaks, and then based on a two-dimensional decision graph, you can manually select the peaks that you would like to use for clustering. So now I'm going to show how this two-dimensional graph works, because it's something that was not covered in the lecture and will appear in this hands-on session. So we can see that here this algorithm is going to find is going to look for clustering in the dataset labeled with A. We have a number of points, each labeled with a different number. And the decision graph is the plot on the B. So what the algorithm does is finding the density, the local density for each of those points. And this is the x-axis on the B plot. While on the y-axis on the B plot, you can see the distance of each of the points from the closest point with higher density. So there's going to be one point in each dataset that is the highest density, that is in the top right of our graph, in this case the point 1. And then in this case we're going to see mainly two peaks, the number 10 and the number 1, which stands for two clusters, the blue and the red clusters. So in this case, we would pick these two classes, the number 10 and number 1. If you wish to have more information regarding this algorithm, we would recommend you to read the paper that you can find written on the screen. We have also seen a number of dimension reduction algorithms in the lecture. So we have seen PCA, which is linear and deterministic, so it has a very rigorous mathematical frame and it has interpretable results. On the other hand, we have seen that it's not able, being linear, to catch nonlinearities. And this algorithm works by finding the principal components, which are those axes that maximize the variance in the data set. So projecting on this plane that is spanned by those axes, you would preserve as much variance as possible from the dataset, losing the least information. Then we have seen one other algorithm that is TSNE, nonlinear, that is nonlinear and stochastic. And in this hands-on session, we're also going to use MDS, multi-dimensional scaling, which is somehow similar to TSNE. The difference is that MDS is trying to optimize the difference between the pairwise distances in the appending and the original space. While TSNE, what it's doing is building some similarity matrix. It's going to build some joint probabilities that says how likely 2 points are to be close to each other. And this trying to optimize these joint probabilities in the appending and the original space, minimizing the Kullback-Leibler divergence. What happens is that MDS focuses on the distance. So distances in a MDS plot are more meaningful of how they would look like in the original space. In TSNE, this does not happen. On the other hand, TSNE is able to delimit clusters with more precision, I would say. So it's easier to isolate the clusters. But if you find distances and if you would like to understand if two clusters are far apart in a TSNE plot and you would like to know if they are also far in the original space, that's not a good algorithm. So for this kind of purpose, MDS will work best. Very briefly, I will show you the different notebooks that we are going to see. So this is the exploratory analysis using unsupervised learning notebook. That is the hands-on notebook for this session. We will firstly find some brief recap of the different algorithms, here clustering and then also appending algorithms. And then later you're going to use to work on this dataset composed of 82 octet binary materials that you might have already seen in previous hands-on sessions. And you're gonna store it using pandas data frames. Then you are gonna define some function for defining actions on these data frames. So here we perform clustering of using the data from this dataset. And later we also below we are going to define a show appending function that builds a visualizer that allows to visualize the different appending algorithms. So this deploys the plotly library that is also the base for a more complicated visualizer that we deploy in the query archive notebook. And this visualizer here is quite simple to understand how it works, while in the query archive notebook is a much more complicated code. And you can already have an example how this works. So by clicking on a button, you can see how the different visualization, and then you can explore your dataset in a much easier way. Then I very quickly, this is the querying archive and performing artificial intelligence modeling notebook. Here you're going to query the archive, and what I would recommend is to apply the same methods that you have seen in the previous notebook onto this notebook. So here we have how the query is performed. You might also change this query. In a subsequent cell, we are going to store the query into a data frame that is our cell. And you might even skip these steps and directly load a cached dataset with these query parameters with this pandas read picker function. And later you can apply your unsupervised learning techniques. So this is where we perform clustering. And in this notebook we use firstly HDB scan and UMAP. You know HDB scan, you don't know UMAP, but you can use your techniques. And I would encourage to deploy the techniques that you prefer, that you enjoyed using the previous notebooks, onto this dataset, onto even another new dataset that you just queried from the Notepad archive. And then you can visualize results using this visualizer. And you can find a very detailed description of how this works on a cell above. So now to conclude this introductory video, in this hands-on session, I'm going to deploy a number of different clustering dimension reduction technique, and then the note we should start, the one that is associated with this introductory video, is the exploratory analysis of octet binary compounds, where you can test these techniques. Then I would recommend that you would deploy such techniques on the Querying Archive notebook, which is also the essence of the AI toolkit. So you should learn some techniques in a notebook and then apply such techniques on a different notebooks, because the AI toolkit is built to facilitate such transfers. Lastly, if you have questions regarding the clustering methods, you might find the AI toolkit, not in the workshop environment, the Introduction to Clustering notebook, that reproduces the results that I showed during my previous unsupervised learning lecture. I hope this was enough for guiding you through this hands-on session, and that you are going to enjoy it. Thank you for the attention.